This project aimed to design and test a complete biomedical signal processing system to acquire and amplify the acoustic output of a stethoscope. The system consists of four key stages: a preamplifier, an adjustable gain amplifier, a low-pass filter, and a power amplifier. The input is a weak analog signal from the stethoscope, and the output is a clean amplified audio signal that can be broadcast through a speaker. Each stage contributed to enhancing the signal's clarity, removing unwanted noise, and delivering enough power to drive the output. Hi, in this segment, I will walk you through the signal processing circuit of the biomedical signal processing system. Using the project schematic, I will explain each stage, component by component, and support it using my Lab 1 and Lab 2 measurement result. Let's begin with stage 1. This is the preamplifier stage using IC1A, one half of the TL072 operational amplifier. The input signal from the microphone or function generator passes through the capacitor C1. This is a 10 microF capacitor that blocks DC signal from entering the operational amplifier and allows only the AC signal through. The two 10 kilo ohm resistor form a voltage divider, creating a 4.5 battery ground, which fires the operational amplifier for single supply operation using a 9-volt supply. The signal is amplified using a non-inverting amplifier configuration. In this setup, R2 is the feeble resistor connected from the output to the inverting input, and R3 connects the inverting input to the ground. The voltage gain AV of this stage is calculated using the formula AV equal 1 plus R2 by R3. This gives us a voltage gain of 23, which is approximately 27 decibel. Now for frequency shaping, C2 and C3 along with R2 and R3 form a bandpass filter, allowing signals within a certain frequency range, mainly between 15 Hz and 1200 Hz to pass, while attenuating frequencies outside this range. According to the measurements I took in Lab 1, when a 1 kHz 200 mV VPP sine wave was applied at the input, the output at TP2 was around 3.3 VPP, which corresponds to a gain of 16.5 or 24.3 decibel, matching what we expect from the frequency response of this stage. Lastly, C4 is used to couple the output of this stage to the next while blocking any DC offset, ensuring only the amplified AC signal is passed forward. Moving to stage 2, this part of the circuit uses IC1B, the second operational amplifier inside the TL072 chip. This stage provides adjustable gain using negative feedback controlled by a trimmer resistor P1. The non-inverting configuration remains the same, and the gain can be tuned based on the feedback ratio set by the trimmer. Just like in stage 1, we use a voltage divider with R9 and R10, both 10 kilo ohm, to provide a 4.5 volt battery ground, since we are still operating in single supply mode. During testing, I applied the same 1 kHz 200 mV VPP input, which stage 1 boosted to 4.6 VPP at TP2. By adjusting the trimmer P1, I fine-tuned the output and there I got a clean waveform at TB3, measuring around 6.1 bpp. If the trimmer is tuned too far, the waveform clips at the supply rate, but I stopped just before saturation. This stage is important because it allows us to fine-tune the amplified signal before sending it to the filtering stage. Stage 3 is our active low-pass filter, implemented using IC2A, another TR072 operational amplifier. This section is configured as a Sallen-Key second-order low-pass filter. R11 and R12 are equal value resistor. C7 and C6 are the frequency selected capacitors. The cutoff frequency is designed to be around 1 kHz. Again, C5 is placed at the input to block any DC signal before it enters the filter stage. This filter allows low-frequency components like heartbeat sounds to pass through while attenuating higher frequencies. Based on our Lab 2 result, we observed that at 1 kHz, the output dropped from 5 volt to 4 volt, which is about minus 1.94 decibel. At 1200 Hz, the output dropped further to 3.4 volt, around minus 3.34 decibel, which confirms our expected cutoff frequency. At TB4, we observed a waveform with reduced amplitude compared to TB3, as expected due to low-pass filtering. This filter behaves as designed, keeping important low-frequency content and suppressing unwanted high-frequency noise. Finally, stage 4 is the power amplification stage, using an LM386N1 audio amplifier to drive the speaker. Unlike the operational amplifiers, the LM386 is specifically designed to provide current gain, which is needed to power a load like a speaker. C13 is a coupling capacitor that blocks DC at the output. C15 helps suppress high-frequency instability, particularly above 40 kHz. The trimmer P2 allows us to adjust the amplitude of the signal going into the LM386. In testing, I applied the output from TB4 around 3.2 bpp and observed the final output at TB5 to be around 7.2 bpp, clean and loud enough to drive the speaker clearly. The waveform remained undistorted as long as I kept the trimmer below the saturation point. This stage ensures that the signal is not just clean, but also strong enough for output through the speaker. Now, I'm going to demonstrate the biomedical signal processing system in the laboratory. This is the fully budgeted biomedical signal processing system. The circuit is powered with a 9-volt DC and receive a 1 kHz 200 mBpp sine wave input from a function generator. Checkpoint 1. Verifying input signal. In this segment, the signal from the function generator is verified at test point 1. This serves as the baseline for observing signal amplification in the next stages. What we are going to see is the waveform after the input waveform passes through capacitor C1. As we can see, it is around 240 mV peak to peak. Stage 1 preamplifier output at TB2. This session demonstrates the output of the preamplifier stage, IC1A, measured between TB1 and TB2. The preamplifier boosts the weak input signal significantly. Expected gain is approximately 23 based on theoretical calculations. Waveform quality and amplification level are observed and measured. So, I connected the probes from oscilloscope with a test point in my circuit. channel 1 at test point 1 and channel 2 at test point 2. As we can see, around 240 millivolt peak-to-peak from test point 1 is boosted to around 3.4 volt peak-to-peak at test point 2 after passing through stage 1. Stage 2 Adjustable Gain Amplifier. This segment shows the output at TP3 across the adjustable gain amplifier using IC1B. The gain is controlled by a trimmer resistor and its effect on the output waveform is demonstrated. The goal is to optimize signal strength without clipping or distortion. Just now we cannot see the voltage values of the output waveform clearly, so I switched the channels for input and output waveforms. Now the purple one is the input waveform and yellow one is the output waveform. Now I use the trimmer to demonstrate its effect on the output waveform. As we can see, it is around 6 volt peak-to-peak. That's the maximum that we can optimize the signal strength without clipping or distortion. Stage 3 Low pass filter output at dB4. In this part, the signal is measured at dB4 through a second order Sallen-Key low pass filter. The filter attenuates high frequency components while preserving the main heartbeat signal range. The change in signal amplitude is measured and compared with expected filter behavior. I adjusted the trimmer at stage 2 to increase the input signal. Since the signal is at 1 kHz, close to the cutoff frequency, the output at dB4 increased, but not fully. This is expected as the filter attenuates higher frequencies, limiting the gain. This confirms the filter's correct behavior near its designated cutoff. Stage 4 Power Amplifier output at dB5. This stage provides current gain to drive an 8-ohm speaker. A trimmer is used to control the final output level, and waveform clarity is assessed. In this final demonstration, TB1 and TB5 are monitored simultaneously. The full signal flow from input to output is observed. Gain, waveform integrity, and overall system performance are verified through real-time oscilloscope measurements. I adjusted trimmer 2 to increase the input to the LM386. As the trimmer was turned, the output voltage at dB5 gradually increased until it clipped around 8 volts peak-to-peak, showing the amplifier's maximum output limit. This behavior confirms the LM386 is working correctly, boosting the signal to speaker, driving levels while clipping occurs when it reaches the supply rate, which is expected in single supply operation. The performance of the circuit was verified at each stage through oscilloscope measurements. The stage 1 preamplifier gave a gain of around 23 as expected. The adjustable gain stage provided turning control up to around 6 volts peak-to-peak. The low pass filter stage correctly attenuated higher frequencies near its 1.2 kHz cutoff. The power amplifier stage delivered a clean signal of 7 to 8 volt peak-to-peak to the speaker without distortion. Comparing TP1 and TP5, the total system gain was about 36 times, showing the effectiveness of the entire signal change. This type of system has real-world biomedical applications. For example, electronic stethoscopes use similar circuit to amplify and digitize heart sounds. In intensive care units, clear heartbeat and respiratory signals are vital for continuous monitoring. Similar circuits are also found in hearing aids, medical recorders, and portable diagnostic devices where signal clarity and strength are essential for analysis or transmission. Understanding this circuit lays the groundwork for applying electronics in real patient care scenarios. To conclude, this project successfully demonstrated a complete biomedical signal processing circuit capable of capturing and amplifying a heartbeat signal from a stethoscope. The system consists of 4 well-defined stages: a preamplifier, an adjustable gain amplifier, a low-pass filter, and a power amplifier. The output was tested using a function generator and oscilloscope. and the measure gain and frequency response match theoretical expectations. Overall, this project highlights key engineering concepts like amplifier design, signal filtering, and practical measurement analysis, which are directly relevant to real-world biomedical applications. Thank you for watching my presentation. This concludes my demonstration of the heartbeat acquisition system project.